right, next up we have Chet Lide. Chet earned a bachelor's degree in geology from the University of Tennessee and a master's degree in geophysics from the Mackey School of Mines. He has previously worked in mineral exploration for Union Carbide, Falcon Bridge Copper, and Great Basin Geophysical. He has 30 years of experience in acquisition, processing, and interpretation of geophysical data, and he is currently the VP of Geophysical Services for Zonge International.
Thanks, Dylan. This talk is really going to focus on observations and the relationship between geophysical measurements and what we presently know about the Cahuilla Epithermal deposit. It's an active project. We are still learning a lot about it. Hopefully these results won't change with the next round of drilling. I'd like to thank my co-authors who have been committed to doing good exploration work in this knee-jerk press release environment that we live in. I'd like to dedicate this to Ken. Acknowledge Terrace Resources for allowing us to publish this and give a talk on it. Mine Development did a lot of the work in the 43101 report. Steve Rispercelli and Andy Walker and Gary Johnson prepared some of the maps. And then the Zonge staff, and particularly the field guys who went out and got the data and allowed me to have a job. The Cahuilla project is located in Imperial County, California, about 30 miles south of Indio, on the west side of the Salton Trough. This is the northern extension of the Gulf of California. The northernmost active spreading center occurs here. The San Andreas Fault comes through here, and the San Jacinto. So it's actively in an active environment. This chunk of ground's heading to the Aleutian Trench. That's the good news. The bad news is going to take 90 million years to get there. It's a low sulfidation hot spring deposit, basically at the surface. It's a very young system. It's altering Pliocene, Pleistocene sediments. Previous workers have included Homestake, Fisher-Watt, Kennecott, Newmont, Consolidated Goldfields, and now Terrace, beginning in 1987. Drilling as of now, there's 347 RC holes for 188,000 feet. Most of that done wet. 21 core holes for 4,500 feet. That's about 2%. Currently, the indicated resource is just over 1 million ounces of gold and 11.8 million ounces of silver. The active work we did this year was mapping and sampling, some geophysical work. The drilling that was done in September and October that we're just getting results on. Our task was twofold. The deposit is two distinct styles of mineralization. One is a flatline tabular zone, replacement zone within the Pliocene sediments. And because a lot of the drilling is vertical and it's RC, they haven't been able to include any of the high grade in the resource estimate. We know there's high grade in there. We're trying to understand the structural controls. Second style of mineralization is deep feeder or deep quartz vein mineralization on the major controlling structure. So we drilled some deep core holes to go after that. The key points, and these are my conclusions, I'm going to tell you now because if I get into Jim's rights time, Dylan's going to brand me with one of those branding irons. So I'm going to give you the points now, let you follow it through the top. But the geophysics shows that the center of mineralization as we know it in Cahuilla is in a complex of intersecting structures. Basically, X marks the spot. The centers of mineralization and the highest grades are spatially associated with high resistivity and high gravity. And this is due to densification due to silicification, something we see in active geothermal environments. Linear trends control the higher grades by suggesting high angle structure within the shallow tabular ore body. And an increased occurrence of pyrite is noted in the center and highest grade portion of the resource, and it's a well-defined IP anomaly is observed beneath the highest grades. This is a geologic map. This is the Modoc Fault. It's the important fault in the area. It separates Jurassic quartz monzonite from Pliocene non-marine plastic sediments. Adjacent to the fault are a series of conglomerates. This is going to be a map frame we'll use for the remainder of the talk. This outline here is the approximate outline of the 43101 resource area. For scale, here's 400 meters. It's 4 kilometers across the map frame. So we're going to get down into this deposit. Other key points are high-grade hill, where previous mining has exploited some sheeted veins within the Modoc Fault. And this area here is the clay shaft, which is in massive kaolinitic vapor clays, altered clay, actually used for pottery. So these will be 2 key points for the talk. This is a center apron, and there's little outcrops of center poking out. This is a 3D view of the property, just to give you an idea. Here's the resource area, this is the flat tabular zone, and this is deeper mineralization within the Modoc Fault. This is the surface trace of the Modoc Fault. We're looking to the northwest. The surface trace of the Modoc Fault comes through here. And this is our center apron. And then something happens and we have everything covered by basically a young band. This is a geologic section put together by Steve Riscoselli. The thing I want to show here is this is looking to the west. Is the Modoc Fault with these are the quartz veins with mineralization. Out here, there's a higher density of veining. It appears to be controlled by horizontal bedding, which is clearly there. What we're looking for is a potential fault or a feeder system that may control some of this higher vein density. I've noted this with a letter A that we'll see pop up on some of the maps in the future. This is the gold block model, basically to show you the general outline of the gold mineralization. You don't really see it that well here, but there is some deeper. It's a slightly higher grade shown here in green. The resource cutoff was 0.008 ounce per ton. That is 2 zeros. This is the silver block model. Again, this shows a little bit better where we're seeing some of the higher grades. There's a couple samples get up upwards of 30 ounce per ton. And it extends a little deeper into the hanging wall of the Modoc Fault. Important physical properties for this deposit are the silicification is the most intense and the widespread alteration type. The gold is directly associated with calcinitic quartz. Argillic alteration is weak, but exists in the Modoc Fault, and then occurs in large areas in the clay shaft area and a belt we can track in the geophysics. Multi-facial quartz veins occur in structural zones associated with the highest grades. Fine-grained pyrite is always present with the gold. However, the grade appears to be independent of pyrite content. A structural study done by Craig Byington in 1989 along the Modoc Fault, he noticed that textural strike inflections along the Modoc resulted in open zones for higher vein density, and noted that the west-northwest orientation was a good direction for higher density. This is some of the core that was recently drilled, just to give you an idea of what it looks like. Multiple phases of chalcedonic veining, brecciation, and a key thing here are many of the veins being at a high angle to the core axis. This is the geophysical data that we'll be looking at. These dashed lines are CSAMT lines run in 1984 and 1994, 1996 for Kennecott. They're done with 30-meter dipoles, 150-meter line spacings, fairly tight. The triangles are gravity stations we acquired in the spring. They're done on 150 meters by to match the CSAMT, 150 meter by 100 meter, and we went to detailed infill in the area where we started seeing things happen. This is a single IP line put across the deposit area, and one of 5 MT lines. We did take a deep look at the structure underneath the deposit. This is a slice map of the 2D inversion results for the CSAMT at a depth of 50 meters below the surface. The center pad is basically in here. There's my letter A, and it's a pretty distinct high resistivity zone within the center pad. We can see some linear trends coming in, and that pretty much is my X. Pretty clear evidence here of a post-mineral fault that offsets mineralization in a textural sense. This out in here, this high resistivity, is actually gravels that's dropping off into a big set of structures here on the east side of the deposit that takes things down into the valley where there's upwards of 7 kilometers of sediments. Here's the high-grade hill shaft and the clay shaft here in what we recognize as a wedge-shaped zone of clay alteration in the hanging wall of the Modoc Fault. We're going to look at the CSAMT section right through that area, through the heart of it. So this is looking east now, northeast, and here's the Modoc Fault. We see the Jurassic quartz monzonite is very high resistivity in the footwall of the fault. This is actually the Modoc Fault zone. This is more or less the footwall where we see the break. We see a wedge-shaped zone of low resistivity associated with some of the argillic alteration in the hanging wall of the fault. High resistivities on the order of 500 ohmmeters. The coloring doesn't really come out that good on this, but it pretty well defines that flat-lying tabular resource. And I forgot to point out to you on the gold block diagram, but the bottom of the gold was at about sea level, and this pretty well shows us a break there. This point right here is an intercept that went 3 ounces per ton, just for reference. Outboard of the resource area, we get into very low resistivity, unaltered sediments in the Pleistocene. So it gets down to less than 5 ohm meters. Okay, so what I've done is I went into the database and I extracted estimates for silica intensity from the core logs, and they've been made consistent for 0 to 4 for increased intensity. So in this case, in all cases you see, the black dots are going to be what has the values of 3 or greater or whatever, and the green dots show the assays that are below that value. So we see a very good correlation between the high indicated silicification and the resistivity, which is not really a big surprise. Tracking out this zone here, we see one hit right in there. These are gold assays. The black ones are 0.1 ounce per ton or greater, and the red ones are where it goes at 1/4 ounce per ton or greater. So there's a strong correlation here with the high resistivities. And interesting west-northwest trends develop here along the Modoc Fault, and then here in Area A, there's my A, which tend to parallel and match the resistivity. To the point where here at the high-grade hill, we trace this zone down, we get into the low resistivity argillic zone, and you can see they drilled for it here, and it's gone. So good correlation between the resistivity and the gold. This is a depth slice at 150 meters below surface, showing the silver. If you remember, the silver went deeper. I didn't get enough gold to make a pattern. But once again, it's correlated and clustering around a zone of high resistivity, which clearly is at a structural intersection. I'd also like to point out, we start at 150 meters, we're seeing a gradient here. This corresponds to a major structure we'll see, and we see things that kind of peel off. Here's our dextral deflection and then taken off on the Modoc. Interestingly, here we don't see this cross fault, and I can't tell you why. Okay, this is the gravity. This is the complete Bouguer reduced at 2.25 grams per centimeter. There's 20 milligals of relief across this area. That's representing the quartz monzonite diving off into beneath these low density sediments. Kind of a not a real featureful map. We do see a bend across the resource area. There's A for reference, and kind of a nose coming down, and that does correspond to kind of a nose in the Modoc Fault. There's our fault from the CSAMT that we think, showing it corresponds pretty well with the inflection in these gradients. But this kind of blah map led some to believe that gravity wasn't helping us. This is the horizontal gradient of the gravity. The horizontal gradient, as most of you know, is an edge picker. Look at it as the Fraser filter of gravity. It's going to trace out your high angle contacts. And here we have it across the Modoc Fault. We picked up this bigger structure, deeper. We see it in the MT. Comes outboard of and inflect, makes a dextral bend or offset here, and takes off to the northwest. Looks sort of like a big dilate zone. These are the structures I've drawn where I see them, just for reference. This is the vertical derivative of the gravity. It is going to enhance the shallower density features and pull out. The highs are going to represent higher density rocks in the near surface. This is shown with the silica and shows a pretty good correlation with the vertical derivative. Indicating to me that we're seeing densification in these Pliocene rocks, increased density due to the silicification. There's A hiding in there. You'll notice lower density or lower gravity in the area of massive clay. Not a real big surprise. Here's the argillic alteration, just simply shows the clay. And not a real big pattern here. We do see it clustered more in the low gravity, and it tends to flank the central high. Here's the gold, just to show that correlation. Once again, gold's following this gravity ridge. It's clustered on this north-south ridge. This is where I think the center of the system is. These wings are drilled and there's mineralization on them. This here was a 10 feet of a tenth of an ounce and some other good grade. It was tried to be twinned with vertical holes. Clearly, there's a lot of room to chase a vein in there with angle holes. Big north-south fault through there, cutting off the system. They've got mineralization right here at 750 feet. There's almost a tenth of an ounce intercept. Where's the man down there? Put my structures on there for reference. Again, the horizontal gradient is picking the edges of things. It's outboard of the high density areas. I believe that it's deeper and that this area is basically in a dilate and jog between these two structures. Here's the IP line that we ran across the area, and I'm showing estimated pyrite from the logs at a depths of 100 to 200 meters below surface. The survey was a 150 meter dipole. Here's the inversion section. We don't have as much resolution, obviously, but we see a wedge-shaped zone, high resistivity. The keel of this thing is below our A area. This is the Modoc Fault Zone. IP, this is the first time I've ever shown an inversion model without a raw data pseudosection to go with it. It's pretty much indicating that I'm starting to believe these things. Or I'm getting too lazy to interpret. A well-defined IP anomaly sitting of 16 milliradians sitting below the keel of the high resistivity in pretty much where the higher pyrite is logged. That's not a surprise either. I believe it's basically showing us the throat of the system. Here's my map of my structures again, and my favorite offset. Here's the MT line that we put across. This is a vector IP, low frequency measurements down to 0.01 to see very, very deep. We got information down to way below what we're interested in. Our ability to invert that data is limited by the line length. Okay, we can't image 5 kilometers down with a 2 kilometer line. Okay, it becomes the same as one sounding. This is the section. The resource area is in here. This is an unconstrained inversion. If I'd been doing a constrained inversion, I would have tried to not make that look like a toilet. This is the Modoc fault as found from drilling. I want to point out, this is a core hole we targeted to test the deep Modoc structure. If you'll recall, that's about where we had a 3-ounce intercept, and I want you to believe that we drilled that on the geophysics. Anyway, so this hole was targeting deep mineralization on the Modoc, and indeed we did hit vein mineralization at 1,300 feet and went into the quartz monzonite at the bottom of that hole. Fairly well imaged by this section. Here is the resource area. These are the 1/4 ounce intercepts on there just for reference. I like 1/4 ounce. This is the location of our outboard gravity gradient. It's in a high angle, low resistivity zone. We can trace that zone for across all 5 of the MT lines. It's clearly a big structure. Exactly how it's related to the mineralization, we don't really know. I'm suspicious that it doesn't have some sort of relationship. Across the top, I've just extracted a profile of the vertical derivative to show you the correspondence of that gravity with the high resistivity, and actually even down to peaking on the locations of the deeper silicification. This segment of the hole is completely, massively silicified. This is a deep feature we're interested in that sits below a very nice magnetic low. It's in your books. I'm not going to have time to talk about it. I think they're heating up that Brandon iron right now. So in summary, the highest grades within the resource area stand out as a complex intersection. I believe that that is the center of the system, and I believe it is at a structural intersection. The highest grades are spatially associated with high resistivity and high gravity when we squeeze the gravity hard enough. And I propose that that's due to densification, due to the silicification of the higher vein density. Linear trends suggest control of the high grade within the shallow tabular ore body by high angle structure, which is what we're trying to define to get the grades up to allow that high grade to be used in the estimate. Recent core drilling, and I showed you in that one slide, shows a lot of veining down the core axis. That was a vertical hole. Increased pyrite is logged in the central and the highest grade portion of the resource, and a well-defined IP anomaly, albeit on one line. That's where being a geophysicist comes in handy. We get these things like that. Is showing us the throat of the system, I believe. The CSAMT data suggests that the resource is offset in apparent dextral sense along a northwest fault, and the southwestern extension appears underexplored. There's a 400 meters of the axis of that that's not tested. And the gravity is defined as subparallel fault zone to the south of the Modoc Fault. It also shows a dextral bend that has been shown to be dilated during the time of mineralization. And I believe or would like to propose that that entire system is in a dilational jog between two major structures. That's it. Thanks.
Thanks, Jeff. Maybe one quick question?
Hey, Gaylord.
Jack, your geologic cross-section, I thought I saw in there a hanging wall towards monzonite.
Very good.
Looked like it was in the middle of the gravels, like a giant slide block.
We don't know what that is. It's been logged in the chips as quartz monzonite, but what we're starting to understand from the core is that it's a conglomerate that has been vein mineralized, and because it was apparently boulder-sized chunks of conglomerate, it was not recognized. If you looked at the holes that actually cut it, one hole said quartz monzonite, the other hole said conglomerate, the other hole said, so we still don't understand it completely, but that's what we think.
Okay, because if it was a solid block, it could have an effect on your density.
It definitely could be our distance.